This video is about friction. Well, until now, we have ignored friction, but it is essential in many things that we do. Without friction, you wouldn't be able to walk or drive or even sit down. Friction can be quite complicated, but we'll use some rather straightforward models. So let's start. Imagine you have a block, which is shown here to the right in your notes, and it's sliding across some surface with some velocity v. Well, friction exists between the two surfaces, between this block and the surface. It's not smooth, it's rough. If you were to zoom right in between the two surfaces, you'd see that there would be these microscopic bumps. So what exactly is happening at these microscopic level over here with these microscopic bumps is actually quite complicated. It involves attractive electric forces between atoms or bonds between these molecules from the upper surface and the lower surface. And as these surfaces pass across each other, these bonds are essentially breaking. And it's quite complicated, and I don't even know if we fully understand it actually. But we're going to use a simplified model of friction. We're going to break friction into three types of friction. We have static friction, kinetic friction, and also rolling friction. Now, I haven't talked about rolling friction in the notes here because I'll talk about that later on when we get into things that rotate. Static friction is the friction that basically keeps an object from slipping or sliding. Kinetic friction is that friction which occurs when the object is moving or sliding across a surface. And rolling friction is a friction that makes essentially round objects roll, like a wheel rolling across a surface. To help illustrate the differences between static friction and kinetic friction, let's consider this diagram that I just put into your notes here. A heavy wooden block being tied with a rope in which you're pulling to the right. And suppose you apply a small force, this force F, to the right, but when you pull to the right, the block doesn't move. Something's resisting it. Well, there must be some opposing force that's acting on the block to keep it from moving in equilibrium. And that's this force that's shown over here, labeled as F sub S, or F sub F S, which stands for the static frictional force. This static frictional force is canceling out the applied force F to the right. They're equal and opposite in directions. If you were to look at the free body diagram for this, you'd have a normal force upwards, force of gravity downwards, the applied force to the right, and the static frictional force to the left. Let's say I decided to apply even a bigger force to the right. Well, what would happen? And let's say that this block didn't move. Well, if it didn't move, then that frictional force to the left would have to be equal and opposite to my applied force. So it seems like this static frictional force is not some set value. It's kind of variable. However, if I keep pulling harder and harder and harder, eventually this block will slide, break away, slide to the right. And that force, just before it breaks away, represents what we call the maximum or peak static friction force. Any force that is bigger than that peak static frictional force will cause the object to slide to the right. If you pull with a force that is less than that maximum peak frictional force, then the object's not going to move. So the object doesn't move if the applied force F is less than the peak static frictional force. So I'll just write this as F sub F for frictional force with an S for static and then max. So if my applied force is anything less than the peak static frictional force, then the object's just going to simply stay at rest. The object starts to slip or move when the frictional force is exactly equal to my applied force. So when the maximum frictional force is equal to the applied force, that's when the object starts to move. So when you apply a force that's bigger than the static frictional force, then this heavy object starts to slide. And the static frictional force that is shown over here is replaced by a kinetic frictional force, represented by F sub F K. To summarize the differences between the kinetic friction and the static friction, I've got this graph here shown to the right, or the bottom right in my screen. Uh, what you can see on the vertical axis is the frictional force, and on the horizontal axis is the applied force that I'm pulling to the right. You see, when I apply 10 newtons of force, then the static frictional force will apply exactly 10 back. If I apply 20 newtons of force, then it applies 20 newtons back. 30 newtons force applies 30 newtons. So all along here, the object is simply at rest. But when I get to, looks like around 39 newtons, if I apply exactly 39 newtons, then the object here starts to move. And so at this point, this is when the object is moving, and this is what we call that peak static frictional force that I mentioned earlier. Now, after you apply, say, 40 newtons of force, then the object is clearly moving at this point. And now another frictional force kicks in. That's called the kinetic frictional force. And you notice that the kinetic frictional force remains roughly constant, and it's actually less than the peak static frictional force. The peak static frictional force in this experiment was about 39 newtons, whereas the kinetic frictional force looks like around, looks like about 29 newtons. So if you apply a force of, say, 40 newtons of force, and the kinetic frictional force can only apply about 29 back, that means that you've got an extra additional amount of force to the right, which causes the object to accelerate. So the kinetic frictional force is a constant. No matter what you apply, if you apply 50 newtons, 60 newtons, 70 newtons, that frictional force for kinetic is actually going to remain constant, whereas the static friction is actually variable. So that's why over here in the equation you'll see a less than or equal sign for static friction, whereas the kinetic friction is actually equal to. Now, you may be noticing some things in here. We need to talk about that. So how do we calculate the magnitude of the frictional force? What are the factors that affect the amount of friction on an object? Well, experiments show that friction depends on solid surfaces. That's the nature of the materials between them. So if you have like steel on steel or wood on steel, the nature of the materials affect the frictional force. Secondly, it's how much these objects are being pressed against each other. That means the normal force. So you can see there's an Fn. That's how much the objects are being pressed against each other. And then microscopically, these type of every material has different types of surfaces, roughnesses to them. And so this factor in here, which we call mu, or the coefficient of friction. It is important to note that it doesn't depend on the contact area. If you were to take a box and put it on the 4 different or 3 different or whatever surfaces that you have, but they all have different contact areas, the contact area doesn't make any difference on the frictional force. So more surface area does not mean more frictional force, which a lot of people have this misconception. The experiments have shown that the total surface area of contact has little to no impact on friction. So friction between solid surfaces in general is independent of the area of contact, as I mentioned in here as important points. The magnitude of the static frictional force basically can have any value between 0 and some maximum peak value right over here, which we call the static frictional force. It depends on how much you apply. If you apply more applied force, then more static frictional force. The maximum peak static friction, so I'll write that as max, is equivalent to mu sub s times Fn. This is mu is what we call the coefficient of friction. It's a Greek letter. There's 2 types of coefficients of friction. There's mu for static and mu for kinetic. Let's go back to the static case here. If you're looking at the peak amount where it's exactly equal, which turned out in this experiment to be 39 newtons, then we use the equal sign. But if you're looking at in general, then we actually have a less than or equal sign, because really you could apply any particular force and have different types of static frictional force. Moving on, as you may note that kinetic frictional force is actually less than the static friction force. So in general, mu k is actually less than mu s. You might be wondering, where do I get these values for mu? Well, these table of mu values or coefficients of frictions can be found in a typical physics textbook. This is a table from your particular textbook. You can see that there's a list of glass on glass or ice on ice or rubber on dry concrete. And so you can see the different coefficients, one for static and one for kinetic. And again, you could notice that mu k is actually less than mu s in every particular case over here. So the coefficient of kinetic friction is always less because, you know, the kinetic friction is in general always less than the peak static frictional force. So this table can be found in your textbook. It's table 4.2. And when you're doing problems, you would have to look it up, the coefficient of static friction. On a test, I would give you those values. You're not expected to memorize these different coefficient values. Also, about the coefficient of friction, it doesn't have any units. You see, the coefficient of friction is equal to the ratio of the force of friction to the normal force. And so if you take the ratio of those two, it's newtons over newtons, which means they cancel out. And so mu is a unitless quantity, has no units. Going to the kinetic frictional force. The kinetic friction force is shown right here. It's always equal to mu k times Fn. Again, as I mentioned, the kinetic friction remains constant. It doesn't change. No matter what you apply as an applied force, it's always going to remain at a constant value. The kinetic frictional force, one important point I should say about this, if you're pulling to the right and accelerating to the right or sliding to the right at constant velocity, the kinetic frictional force points in the opposite direction that the object is sliding. It's essentially parallel to the surface in the opposite direction it slides. And usually that's the easier one to determine because if it slides to the right, then the frictional force is to the left. If it slides to the left, then the frictional force is to the right. The one that's a bit trickier is the static frictional force. I just maybe want to talk about that for a little bit. Suppose you have a block that's sitting on an inclined plane. If you were to draw the free body diagram, you would have the weight going straight down, the normal force perpendicular to the surface, and then what about friction? Well, if it's stationary, it's got to have some force that's keeping it from sliding down. The frictional force would be acting parallel to the surface. All frictional forces are parallel to surfaces, but it would be in the opposite direction that it tends to slide. See, the frictional force, the static one, points in the direction to prevent the object from slipping. So because the object tends to slip down the incline, then the static frictional force will be pointing up parallel to the incline. Now let's suppose that the block was moving along the incline. Let's say it's like sliding up the incline with some velocity v, and it's actually probably slowing down. So in this case, because it's moving, it's not static anymore, it's kinetic. What direction would the frictional force be acting in this particular case? Well, hopefully you realize it's going to be parallel to the surface, but in the opposite direction that it's moving. So as the object slides upwards, the kinetic frictional force will act in the opposite direction that it's sliding. Now suppose that this object is now sliding down the incline. So as it slides down the incline, what direction is the frictional force in this particular case? Again, we have that sliding or kinetic friction, and the friction's always in the opposite direction that it moves, which is going to be up along the incline, parallel to the surface. So hopefully you're starting to see it can be a little bit tricky. Let's take a look at one more example. So let's suppose you have a truck moving to the right or accelerating to the right, depending on the situation, and it's got a crate or a box sitting on the truck bed. And the question I am asking is, what is the direction of the friction in these different scenarios? Let's suppose the truck is simply at rest, and then it takes off very quickly from a light and starts to accelerate to the right. What direction is the frictional force in this scenario? We know that the box has to accelerate to the right. That means that it must be an unbalanced force to the right. If we were to draw a free body diagram for the box, you'd have an upward force, the normal force, and a downward force, the force of gravity. But more importantly, what direction is this frictional force? Well, if the truck or the box have to accelerate to the right, then that means there must be some force that is acting to the right. And that's a frictional force. Now, because the block, I'm assuming that the block or the box is not slipping off the truck bed, it's remaining stationary relative to the truck bed, then this is actually a static frictional force to the right. And it would change depending on what the acceleration is. Now, if the truck accelerates so quickly that it exceeded this peak amount of static frictional force, then the block would actually accelerate backwards, or it wouldn't be able to accelerate in the forward direction. It actually remain stationary in that scenario. Let's say that the truck then suddenly came to a halt. Now my acceleration is not to the right, and we don't have a frictional force to the right anymore. It must be pointing to the left. So now the frictional force is actually pointing to the left. So static frictional forces tends to be a bit tricky. You have to think about it about kind of like it tends to oppose the direction where it's trying to move. It's trying to prevent it from slipping. So if it's going to slip backwards, it's going to provide a force forwards. If it's going to slip forwards and run into the truck in the front end of it, then it's going to provide a force in the opposite direction to the left. So it's a little bit tricky, as you can see, with friction, but I just wanted to give you a couple of examples so that you get the idea of the direction, how to calculate the magnitude, and what does it depend on? The coefficient of friction and that normal force, which is that surface, how much these surfaces are being pressed together against one another. Okay, I think you're ready to tackle some problems now.